Hi, my name is Tajamul Ashraf, and I'm a graduate student at Indian Institute of Technology, Delhi. And today I'm going to present our work accepted in FACV 2024 titled TransFed, a way to epitomize focal modulation using transformer-based federated learning. Transformers in federated learning. Transformers employ self-attention for comprehensive global interactions, enabling the model to selectively focus on relevant parts of the input sequence for an output element. This mechanism is effective in capturing long-range dependencies in data, making it resilient to shifts in medical image analysis especially. Federated learning, on the other hand, is a machine learning paradigm that enables model training across decentralized devices or servers holding local data samples. Nowadays, the self-attention mechanism is harnessed in federated learning to enhance model performance, which in turn became a motivation for us to delve deeper in this area. FedAvg algorithm, as shown in Figure 1, facilitates collaboration among decentralized clients by averaging their local model updates. The synergy aims to address challenges related to non-ID data distributions and enhance the learning process in decentralized setting. Focal-based transformers. A recent transformer architecture which replaces self-attention by focal modulation for modeling local interactions into vision tasks. It comprises of broadly three components: focal contextualization, gated aggregation, and element-wise affine transformation. It first aggregates context focally and then each query and then adaptively modulating the query with the aggregated context as shown in figure 2. Expanding on this observation, we conducted an inquiry into the impact of focal modulation in federated learning. The experimentation involved three different models: local transformer, FedAvg transformer, and vanilla-tailor transformer. To experiment with, we sampled a set of images from a RSNA pneumonia dataset using the attention rollout technique. Our assessment indicates that both the local transformer and vanilla-based transformer models adeptly identified crucial information in the image, which are indicated by the yellow regions in the figure. At the same time, FedAvg transformer was unsuccessful in generating meaningful focal modulation maps. In the context of visual tasks, the TransFed framework incorporates the utilization of traditional dyno model. So coming to the problem statement, for the purpose of emulating a federated scenario, we examine a collection of n clients with each client L holding its own dataset DL. The customized model associated with client L, defined by the parameters theta, is denoted by a function of theta and the parameter. The optimization of objective is given in the equation below, where the theta represents a set of tailored parameters for each client, and k denotes the per sample loss function that is common to all clients. The selection of the loss function for a specific task, whether it's mean square error or cross entropy loss, is contingent upon the nature of the task. Using focal modulation directly on client layers can harm performance with diverse data as shown earlier. To address this challenge, our solution involves tailored focal modulation. This approach entails customizing certain layers while aggregating other layers to maintain standard insights. Figure 5 illustrates the fundamental configuration of the vanilla focal modulation. Customization in transferred parameters are locally trained and aggregated on the server, similar to FedAvg algorithm. This process is repeated for multiple communication rounds. The learnable generator at the server end, denoted as H and parameterized by phi, takes an input learnable embedding vector Z associated with client I, which can either be a client-specific embedding or a fixed vector. We implement the learnable generator using simple fully connected layers where each transformer block last layer is unique. The learnable generator produces the production matrix Pi for each client I, which are decomposed into query, key, and value projection matrix for the focal modulation mechanism. This approach enables the learnable generator to learn a set of projection parameters Pi for tailored focal modulation. Contrasted with the standard customization method, the learn-to-tailor approach within TransFed brings forth a range of benefits. Firstly, it achieves effective parameter sharing across each client. Secondly, its scalability accompanies an expanding client base. And lastly, its adaptability extends in new clients whose data remains unseen during the training phase. So we conducted experiments on two widely used pneumonia benchmark datasets, Gillani and RSNA. We utilized two partitioning techniques to emulate non-IID scenarios in our experiments. As non-IID distributions better represent diverse user data, contributing to a more realistic evaluation of federated learning methods. The first strategy, the pathological setting, involved randomly assigning classes to each client in the Kermanian RSNA dataset. In this setting, the sample data for class C on client was randomly generated from a uniform distribution. The second approach consisted of generating a federated version of the dataset by randomly partitioning samples with identical labels across clients. This partitioning was done using a symmetric beta distribution. To enhance the realm of the local datasets within the Kermani dataset, we employed a two-stage pachinko allocation method. So table 1 provides a summary of datasets, their allocated tasks, as well as the counts of clients and the model involved in this work. In our evaluation, we comprehensively compare TransFed with various federated learning algorithms. We compare TransFed against fundamental federated learning algorithms, including FedAvg and FedProx. Additionally, we evaluate its performance against state-of-the-art customization algorithms, including FedPer, pFedMe, and FedTP, and as well as the vanilla-based models. By including these model algorithms in our comparison, we aim to assess the effectiveness and superiority of TransFed in achieving customization and effective federated learning. The selected algorithm represented a range of approaches that tackle different aspects of customization in federated learning, which allows us to evaluate TransFed's performance with basic and advanced techniques. The test accuracy in these all methods is shown in figure 6. We conducted a comprehensive performance comparison between TransFed and several well-known federated learning methods, which were designed initially based on the CNN backbones. So table 2 displays the average test accuracy of these algorithms, highlighting TransFed's remarkable performance superiority over each of them. The FedAvg algorithm could impede the distinctive client representations with the transformer models, as evident by the local T outperforming FedAvg transformer model. As depicted in the table 2, the TransFed model consistently outperforms all the models, and especially vanilla customized transformer across all settings. Now, analysis of the different adapted paths. The study examined the effects of personalized various components of the transformer model. Especially, we focused on 4 components: the customized focal modulation layers, which was our proposed method, the multi-layer perceptron layers, the normalization layers, and the encoder layer. To maintain a fair comparison, we employed the learnable generator to generate parameters associated with these individual components while ensuring consistency in the focal net structures as described. The results of the experiment are shown in table 3. It's evident from the table that the personalized focal modulation layer yields the best performance compared to personalizing other components. We thoroughly assessed our method's capacity for generalization, contrasting it with pFedMe and other methods, and its approach on Kermanian RSNA datasets under a beta distribution. To simulate a realistic scenario, 30% of the clients were randomly selected as novel clients whose data had not been seen during the training phase. In table 4, as you can see, the outcome suggests that transformer learnable generator exhibits improved resilience and adeptly adjusted to the new clients in just a few epochs. To thoroughly examine the impact of learnable generators, we conducted a comparative analysis by doing an ablation study between TransFed and vanilla customized transformer model. The latter method restores the projection matrix PI for each client locally without the utilization of learnable generators. To delve deeper into acquired client embeddings, we utilized T-SNE algorithm for projection on a 2D plane, as shown in figure 6, which clearly shows that a distinction between the two classes across all clients. In our comparative analysis, we did our experiments on CFAR and CFAR 100 datasets. Transformer consistently demonstrates superior accuracy rates. This distinction performance advantage is particularly evident when considering various client populations encompassing 50 and 100 clients. So, at last, concluding this video, we introduced TransFed, a transformer-based federated learning framework that addresses the limitation of focal modulation in non-IID scenarios. TransFed overcomes the degradation of focal modulation under traditional federated learning average algorithm by adapting to customized focal modulation for each client with the use of a learnable generator. So, while TransFed's training speed lags behind CNN models, ongoing research aims to ensure its computation and communication efficiency. These are some of the references we used. Thank you so much for watching this video.